Hello to everybody. I am Danilo Col from NGSoft, and I'm the product manager of TrueLoad for the European market. First of all, thanks for your participation, and welcome to the webinar about string gauges and TrueLoad. The webinar covers the string gauge fundamentals and the use of the first-to-market TrueLoad software. I'm happy to introduce you Tim Hunter, who is the president and the founder of Workbench Technologies. So, please, Tim, I give you the role of presenter.
So our software here is about helping users generate loads, and what you see here is a project that was done by some university students here in Milwaukee, Wisconsin, in the USA. So these students here want to basically understand the loading on their suspension arm for their Baja car in order to redesign and lightweight their car. So this is a fun project we worked on with the university, and we'll get to this towards the end of the presentation. So this is all about TrueLoad and our flow here. So TrueLoad basically is all about letting you leverage the FEA model and the test data to work together to understand your product loading. So these are all examples of customer applications that we've done in the past, and really the products from Wolfstar Technologies are our flagship product, which is TrueLoad. TrueLoad turns components into load transducers, and we do this by selecting strain gauge placement on the FEA model. We'll extract a correlation matrix that relates strain response to unit load cases on the FEA model. You place strain gauges on the physical part and measure the time histories of strain, and then we'll take those measured time histories of strains and turn those into time histories of loading, leveraging the correlation matrix we extracted. We're basically turning your parts into load transducers by leveraging the FEA model. The second tool from Wolfstar Technologies is a product we call TrueQSE. QSE stands for quasi-static events. And so quasi-static events are basically linearly superimposing individual result sets from the FEA model via user-defined functions. And that's great by itself, but what happens with TrueLoad is we're going to create time histories of loading from your measurements, and now we're going to take those time histories of loading then and use TrueQSE then to reproduce any stress or strain at any node or element you want, or we can generate operating deflection shapes. So TrueQSE is basically the post-processor for the loads you measure with TrueLoad. And TrueQSE is so important in the whole technology that when you buy TrueLoad, you get TrueQSE automatically. So we bundle those together. And then the third product from Wolfstar Technologies is a product we call TrueLDE, and that stands for Linear Dynamic Events. And this is solely an analysis-only solution, and it's really about letting you have a better post-processor for your linear dynamic solutions in the time domain, frequency domain, or PSD domain. So it's basically an easy-to-use post-processor tailored just for those applications. And it's an analysis-only tool. And then if any of you are doing FEA-based fatigue, then the tools from Wolfstar Technologies automatically interface to FEA-based fatigue softwares, because we're all about getting the loading right. And now that you've got the loading right, we can now drive those into your FEA-based fatigue softwares, and we basically generate the loading data and a macro that sets up your FEA fatigue software automatically, so you can do FEA fatigue very, very nicely and automatically. You don't need to have FEA-based fatigue to use our software, but if you do, we make using your fatigue software much easier. Okay, so this is just a snapshot of our customers. This is actually from our website, and this slide is actually pretty old. We've got several more customers on the slide now, but this is basically showing our customers that are using our products and services. The highlighted customers have all benefited from TrueLoad. Either they are customers of the TrueLoad software, or we've done consulting projects with them using TrueLoad. Okay. So what's going on here? So a little bit about Wolfstar Technologies. It was founded back in 2010 by me, Tim Hunter. I'm the president and founder. Prior to founding Wolfstar Technologies, I was 22 years at Harley-Davidson, where I was chief engineer of vehicle structures. I've been involved with every aspect of product development. We fully understand what it takes to develop product. We understand the struggles that you go through. Since launching Wolfstar Technologies, we've had excellent relationships with our partners, Dassault Systems, ANSYS, MSC, and CE-Tron is our visualization tool that we use for all of our 3D visualization. So these are software partners that see what our software brings to our customers, and they want to get it into your hands as quickly as possible because they know it makes you a better user of their products. So the whole motivation behind TrueLoad is quite simply, what's the load? So if you're a design engineer working on this motorcycle and you've got design products that are durable and function properly, you need to understand the loading. But the loading here is extremely nonlinear. You can't measure the loading. You can't simulate the loading. But you as the design engineer are being held responsible for designing products that function and are durable. So what do you do? So quite simply, we recognize that the individual components are basically responding linearly. So the swing arm, the frame, the crankcase, the handlebars, the fenders, the gas tank, the luggage systems, these are all basically responding linearly. So we can place strain gauges on these individual components and subsystems and use those strain gauges then and the TrueLoad technology to back calculate the operating loads in the structure. And now that we've got those operating loads, now you can do design and optimization with the loads to design the parts properly. So that's what TrueLoad's all about, is getting the loading so you can do redesign and understand what's going on in your structures. This is a first-to-market solution. It's based on a technology called influence coefficients, and that's been around for 40 or 50 years. But the problems with influence coefficients historically is that it's been an all very manual, experimentally based technique. And so strain gauge placement was guessed at, and the setting up the loading in the lab was very expensive to do. And this is all now taking the FEA model and leveraging the FEA model through scripting in order to get the proper strain gauge placement and the optimal correlation matrix. So TrueLoad is basically getting you a tool to basically turn your part into a load transducer. So historical concerns with loading. You can have a perfect FEA model, perfect CAD model, perfect mesh, perfect solver, but oftentimes when an analyst goes in to use their FEA model, is when they go to throw it in for the solve, they'll guess at what the load case is. And if you're guessing at what the load case is, you're basically guessing at the results. So in the US, we've got this term that we call GIGO, garbage in, garbage out. So if you're just guessing on the inputs, you're guessing at the outputs. So people try to get better understanding of the loads using load transducers like you see here, and these are fine, but the problem is that they're expensive. And every time you use one of these, you've got to modify your structure. You've got to cut out part of your structure, insert the load transducer. So now you've just changed the stiffness, you've changed the mass, you're measuring something. It may or may not be the actual loads. And now when you bring to the analyst is typically working on the as design part. And now the analyst has got to rework their FEA model to look like the test part in order to use the loads you just measured. So this isn't great, but this is traditionally what people have got to do to understand loads. And then another approach that people try to use are strain gauges. So typically an analyst will look at your FEA model. They'll come up with some strain gauge locations for placing strain gauges in the model. They'll talk to a colleague, come up with some more locations. They'll get 30 strain gauges of data laid on the structure. They'll go to the proving grounds, bring back 500,000 data points of data from the proving grounds, and they look at the data and they look at the FEA model, and they can't make any sense of it. So typically, they'll throw out all but 1 or 2 channels of data at 1 or 2 points in times, and they'll work for days, if not weeks, to get a test case, a load case on their FEA model that makes those 2 strain gauges light up in the same direction, just qualitatively, not even quantitatively. They'll use those so-called correlated loads now to redesign the part. And now the next time they get to the field and they do the testing on their redesigned part, they find they've missed something or they're getting the same problem all over again, and they've got to repeat the cycle, okay? So this is very typical. I've done this in my past. I'm sure many of you have done this type of thing too. This is just a fundamental problem with FEA modeling and testing. So what's wrong? You got great analysts, you got great software, you're doing the right stuff by testing, you're doing the right stuff using FEA-based fatigue. So you're doing all of the right things for doing the analysis and stuff, but you're not getting it right. Well, what's going on? Well, quite simply, you've just got too many variables to manage. You've got the gauge locations, you've got the load cases, the quantity of data. So if you've got 30 channels of data, and these 30 channels, you've got 500,000 data points in your time histories. The problem is at each point in time, there's a unique loading recipe to reproduce a strain field at that point in time. So now you've got 500,000 data points, you've got 500,000 recipes. This is just something that you can't do manually, and you're just left in this no-win cycle, okay? This is just a hard problem, and it's hard to solve manually, okay? So the solution here is TrueLoad. TrueLoad is doing what's called in-situ load measurement. So in-situ means in-location load measurement. So we're going to turn your components into multi-channel load cells by leveraging the FEA model to work with the test data. We can work with any FEA. We've got great plugins for ANSYS Workbench and Abacus CAE. But at the end of the day, we're going to get you optimal strain gauge placements, and we'll get you an optimal correlation matrix, and we got a great interface to the major FEA-based fatigue packages. So this is what we're all about. So this is a very typical thing in the automotive industry to have this V diagram for product development, where you start with the voice of the customer and come up with your product requirements and specs. Then you get into the CAD and FEA, where you're doing system, subsystem, and component design. So this is on the virtual side of things. And then when you want to start proving out your product, typically you start at the component test and work your way up some subsystem, system test, all the way up to the full product test there. And what TrueLoad's doing is we're taking the test data from the test side of the development cycle here and bringing it back into the virtual world so that we can bring it in and do better jobs at simulations, so that we can do a better simulation and go through this iteration cycle fewer and fewer times. So here's a workflow for TrueLoad. We're going to start off with some unit load cases on the FEA model. So rather than a complex load case, I'm going to have you come in and do unit load cases. So this could be 1 kilonewton in the X, 1 kilonewton in the Y, 1 kilonewton in the Z. Could be a pressure load, a thermal load, or inertial load. But at the end of the day, you have to think about these unit load cases and say, could I mix them together, and would this approximate the operating environment? And then once you solve that FEA model, the pretest software looks at the strain results on the FEA model, comes up with the optimal strain gauge placements, and now there's tools that lets you reposition and reorient those gauges to make them easier for the test department to lay. And then at the end of the day, then once we're happy with the gauge placement, we're going to extract a correlation matrix that relates the strain response at these strain gauges to each of the unit load cases on the FEA model. So we'll store the correlation matrix to disk, we'll take our gauge placements and go to the lab and place strain gauges on the physical part now. And now we can do strain measurement anywhere we want. This could be in the lab, this could be in the proving grounds, it could be in the customer's hands. So however you want to do the strain measurement, you just go out and collect strain data and get time histories of strain. And then we take the measured strain data and we bring it in the post-test environment now. Post-test is going to take the measured strain, multiply it by the correlation matrix from pre-test to generate loads. And now we've got nice time histories of loading functions. And loads are loads are loads. You could bring those into your FEA model like normal. Or what I highly recommend is use the TrueQSE tool, which is going to organize all the unit loads and the corresponding loading functions automatically and very quickly and very efficiently allow you to generate operating deflection shapes and any detailed stress or strain analysis on any part of the top your FEA model that you want. And once you've done that, you can always then go off and do FEA-based fatigue, because now you've got strain correlated loading functions, which are the hardest thing to get for your duty cycles. So now you've got proper loads for your duty cycle, and now you can do FEA-based fatigue analysis, okay? So this looks kind of complex, but really the first 4 blocks are you turning your part into a load transducer. The bottom flow chart is you doing design and optimization once you've got your loads. So you might do the top one once to get the loads and go through the bottom flow chart 20, 30, 40 times as you design and optimize your part. Okay, so we basically have got customers in all of these product segments. So we're helping our customers get loading from the wind, sea, or air, from the customer themselves, from internal loads. We can get loading on just about any structure out there that you could possibly be working on. It's all based on linear systems and loads. So linear systems are where loads are proportional displacements, displacements proportional strains, strains proportional loads. This is a linear system, okay? So I understand everything in life is nonlinear, but what we're doing, we're turning your part into a load transducer. So we're going to stay away from hotspots. We'll stay away from welds. We'll stay away from bolted joints. We're going to stay away from pin joints and areas of contact. We're going to be in nice nominal areas in the part. We just need the strain response to remain proportional. The loading can be as nonlinear as anything. It could be sinusoidal loading, ramp loading, impact loading, whatever sort of loading happens to the part is fine. I just need the strain response to remain proportional. So I can take this diagram and turn to a couple of equations. So the right-hand side, well, this is F equals Kx. So this is Hooke's law. So if your part is obeying Hooke's law, then the left-hand side of the triangle has got to apply, where strain times C is equal to the load. So this is basically a strain corollary of Hooke's law, and we're going to calculate loads as being strains from test times a correlation matrix from FEA. So this is what we're doing. Okay, so just one more time through the workflow, and then we'll get into some customer examples here. So this is an example that I do in my training classes with my students. So this analyst is working on a headlamp on a motorcycle, and this headlamp is undergoing excitation from the front wheels and suspension, from the handlebars, from the engine and frame vibrations. So the analyst looks at this part and says, oh, this is basically a base excitation problem. So he's going to model it as being restrained to ground at the bolt locations, and then having 10 Gs X, 10 Gs Y, and 10 Gs Z applied on the structure. So these are his FEA model unit load cases he put on the structure. And then he just goes into the pretest software, and the pretest software loads up his 3-unit loads for him automatically. And then he selects a subset of the model to place strain gauges on. So he's going to select areas in the middle of the headlamp and in the middle of the legs here, and he's going to stay away from the boundary conditions, and he's going to stay away from where he's got rigid body elements connecting the structure together, because he wants to be in nice nominal strain areas on the structure. Okay. So this is the user's choice here on where he's selecting possible places to lay strain gauges. And then he tells the TrueLoad software he wants 6 strain gauges, and TrueLoad goes out and draws up the strain gauges on the structure as being these lines showing the position and orientation of each gauge. And once he's happy with that, then he goes off and collects the measured strain data. And now the whole point is we want to take these measured strains now and turn them into loading functions, and we're going to do that through post-test. And post-test basically brings in the C matrix from pre-test, it brings in the strain data from test, and he pushes a button to generate the loads. It's really that simple. There's things in here to map and drop channels, to plot data, but really all it is we're bringing the C matrix from pre-test, the strain data from test, and you're pushing the button. And when we push the button here, it's going to take the measured strain data times a correlation matrix to generate the loads, and then post-test is going to generate an HTML report for us that's going to talk about the quality of the loads we measured. So it's going to go in and calculate the simulated strains at the strain gauge locations in the FEA model, generate an HTML report for us, the strain correlation, and it's going to generate for us one of these true QSE files where it'll have each of the unit load cases and the corresponding loading functions connected, and then we can probe any node or element for any results we want, or generate operating deflection shapes, or go off and do fatigue analysis. So it's really that simple, okay? All right, so let's show you how this looks like in Workbench. In Workbench, we basically would have our structural analysis here, and then when we want to find strain gauges, we'd bring in the pretest task, and we'd use pretest to define the gauge placement on there. Once we're happy with the gauge placement, we'd go off and do some testing. In this example, I've got 3 sets of tests here. We run post-tests on each of those tests to generate the loading. Now that we've got the loading from post-test, we can bring in our quasi-static events, and we'll to each one of these post-tests to generate our operating deflection shapes and query the model however we want. And then if we wanted to set up a duty cycle, for example, we can go in and bring these into our duty cycle manager, where we can say, you know what, we've got 10 repeats of the first test, 20 repeats of the second test, and maybe 5 repeats of the third. So we make a nice duty cycle here, and the duty cycle manager then will send this all off to our fatigue software then to generate fatigue analysis. So this is how it looks like in Workbench. Okay, so we're getting close to the end here, but I wanted to just show you some of our customer examples here. So this is Aaron's. They're makers of these lawnmowers, these zero turning radius lawnmowers. And basically, they talked to us to see if we could help them redesign this engine deck here that sits underneath the seat. And so working with them, we basically set up a model, and we decided that this is a basic citation problem. So we put 10 Gs, X, Y, and Z on the structure with the lump mass of the engine here. The TrueLoad said place strain gauges in these 8 locations here in the structure. And we took those 8 strain gauges and we instrumented up their structure. And what you see here are the strain response of the 8 strain gauges going over their proving grounds. And we take those 8 strain gauges times a correlation matrix to generate the loads. And now that we've got the loads, we can go back inside of the structure and pull out the simulated strain on the structure at the strain gauge locations and plot those up in blue. So these are all 8 gauges. Green is measured, blue is simulated, they're line in line. Here's a cross plot showing measured strain versus simulated strain. So, and once we've got that, then we can generate an operating deflection shape, and this is fantastic. Now, what's great about this structure, this company had decided to do their redesign their own with their best design practices. And when they showed us the structure on their shaker test, it had broken an hour before we got there, and it broke in 12 hours. It was supposed to go 10,000 hours. So we took their FEA model, ran that through TrueLoad with the loads that we measured, and you can see the strain responses that they're getting there. And then working with the engineers, we came up with a new design iteration, and we changed around configurations. And by the end of the week, we had a new design that was working for us. And let me show you the durability plots here. So here's their fatigue material. Their goal is to go 10,000 hours, so we want to see yellow, green, and blue in these plots. So the baseline model was working fine. There's some red here because of our RBE. Now there's their structure that failed in the lab in 12 hours. The fatigue software said it should last 10 hours. So we're getting a perfect correlation here with the loading we've applied to the structure. And then using that same load history now, we've come up with a redesign. And by the end of the week, we've got a redesign that gets them all the loading they need, all the loading they need to do redesigns properly, the airflow they need, and they've actually got better durability than they started off with. And when we talked to the engineers at this company how this went, they said if they did it traditionally without TrueLoad, each design iteration cost them $30,000, 6 weeks to procure the parts. So we did 5 iterations, $150,000 in 30 weeks. And with TrueLoad, we did all that in 8 days and under $1,000. So this is some of the benefit and cost benefit analysis you get. Okay, and one more example here, 2 more examples. This is a bulldozer from a customer. So just wanted to show you how we can use this technology to get loads on the bulldozer. So here we had XYZ loads on the front of the blade. We had a load on the hydraulic cylinder here, and there's a mechanism on the back. We had 5-unit loads. We placed 12 strain gauges on the structure here, some on the arms, some on the back of the blades. And again, you're seeing my green and blue plots on the right here, where green is measured, blue is simulated, and we're showing how good we're getting correlation. Now, this company was really concerned with these forgings here, where they had issues in development, and so they placed extra gauges on here, like this gauge number 19, which is a gauge right in the hot spot here. And so we got gauge number 19 plotted up in green here, and then we probed the structure using TrueQSE to get the strain response near the weld, and you can see how well we're matching that strain response. So this is just a nice demonstration that shows once you get the overall loading right, the hot spots come along for the ride. And this is our final example, okay? Just a few minutes on this Baja car. So these students here that are working on this Baja car, they came and talked to me that they wanted to use my software to help them redesign their Baja car. And so what they did is they set up some loads on an FEA model. So the XYZ loads are the shock, XYZ loads the wheel, X and Y loads the stabilizer links. And so they basically, at the end of the day, they had 11-unit load cases on the structure. These are the animations of their unit load cases. And then the TrueLoad software told them to place strain gauges in these locations. So we got some gauges on the arms. Most of the gauges ended up being on this forging here, because that's where most of the load paths are. So again, the gauges end up going on the load paths. And then they instrumented everything up. Now I have to emphasize here that these are a bunch of students. There was 1 graduate student and 2 undergraduate students working on this. These guys have never built a real FEA model. They'd only used FEA models in class. So I helped them out with the FEA model. I coached them on how to set up the FEA model. They had never touched a strain gauge. They had never done any data collection. So I coached them and helped them out here, but they did everything on their own, and they did this from beginning to end in 6 weeks. They even built some jumps, and they turned the parking structure of the university into their proving ground. So we're collecting data over this jump here, and we did some other maneuvers in here, some maximum brakes and hard turns, and we're collecting data on all this stuff. And then here's the true load results. So the green curves are their 16 channels of strain data here. So we take the measured strain data here, these green curves, we multiply it by the correlation matrix, and now we're getting time histories of their loading functions. And now that we've got the loads, then we can go back into the FEA model and pull out the simulated strains at the strain gauge locations to plot up the simulated strains. And then we got a nice cross plot of measured strain versus simulated strain. So this is near perfect strain correlation here. And they did this from beginning to end in 6 weeks from a bunch of college kids who've never done anything before. And here on the bottom right here, you're seeing the operating deflection shape of the structure now that we've got the loads. And then once they've got all that stuff, then they wanted to do some redesign. So they basically made up a duty cycle of how many hard brakes, how many hard turns, and how many jumps they had. So they had a 5.6 hour duty cycle. When they ran it through the fatigue software the first time through, they were getting 278,000 repeats. So that was more than they needed for a test for a race bike, for a race vehicle. So they basically went through and they thinned up the tubes, all except for this diagonal tube. They thinned up all the other tubes, and they were able to get their weight down by 25% and still be able to have 12,000 repeats, which is more than enough than they need. And so they were able to do this very quickly within a couple of days to reduce the weight in the structure. Okay, so 25% weight savings on an unloaded structure on the Baja car is a very, very important thing. And they wrote all this up in the SAE World Congress back in 2017, and there's a paper on that you're happy to go get. Okay, thank you. I think I'm done here. So Danilo, I'd like to turn it back over to you. I don't know if there's any questions coming from the audience, but I'm happy to answer anything you might have.